Hello and welcome to another video. In this video we're going to discuss the transport layer security, or TLS, and it will be actually focusing on version 1.3 and some vulnerabilities related to that version. So to begin with, let's start with what TLS is. The transport layer security is a protocol that provides authentication, privacy and data integrity between two communicating computer applications. It is the most widely deployed security protocol used today. It is used for web browsers and other applications that require data to be securely exchanged over a network, such as web browsing sessions, file transfers, VPN connections, remote desktop sessions, and voice over IP. TLS evolved from Netscape's Secure Socket Layer, or SSL protocol, and even though the terms SSL or SSL TLS are still sometimes used, it is more often used rather than SSL. Key differences between SSL and TLS that makes the TLS a more secure and efficient protocol are message authentication, key material generation, and the supported cipher suites, with TLS supporting newer and more secure algorithms. TLS and SSL are not inoperable, though TLS currently provides some backward compatibility in order to work with legacy systems. There are some attacks against TLS. Even against the earlier versions there are a lot of attacks, so implementation flaws have always been a big problem with encryption techniques, and TLS is not an exception. The infamous Heartbleed bug was the result of a surprisingly small bug in a piece of logic that related to OpenSSL's implementation of the TLS Heartbleed mechanism, which is designed to keep connections alive even when no data is being transmitted. Although TLS is not vulnerable to the poodle attack because it specifies that all padding bytes must have the same value and be verified. A variant of the attack has exploited certain implementations of the TLS protocol that don't correctly validate encryption padding byte requirements. Finalized in 2018, TLS 1.3 is the current version of the protocol. TLS 1.3 was developed to address various vulnerabilities that have been exposed over the past few years, reduce the chance of implementation errors, and remove features no longer needed. For example, MD5 cryptographic hashes are no longer supported. Perfect forward secrecy is required, and RC4 negotiation is prohibited. All known vulnerabilities against prior versions of TLS, such as Beast, Crime, and protocol downgrade attacks, have also been eliminated. Popular web browsers such as Google Chrome and Mozilla Firefox use TLS 1.3 by default, where possible. In 2018, the payment card industry data security standard, the industry that regulates governing the protection of electric card transactions, mandated the use of TLS 1.1 or higher in most situations. In addition to the enhanced resilience, TLS 1.3 is faster due to the more efficient handshake between the two systems communicating. Some major improvements of TLS 1.3 over TLS 1.2 are the separation key agreement and authentication algorithms from the cipher suites, removing support for weak and lesser used names elliptic curves, removing support for MD5 hash and SHA-224 cryptographic hash functions, requiring digital signatures even when a previous configuration is used, integrating HKDF and the semi-ephemeral DH proposal, replacing resumption with PSK and tickets, dropping support for many insecure or obsolete features, including compression, renegotiation, and so on, prohibiting SSL or RC4 negotiation for backwards compatibility, integrating use of session hashes, deprecating use of the record layer version number, and freezing the number for improved backwards compatibility. TLS 1.3 is a major update of the standard that improves speed and significantly improves security. One of the main advantages of TOS 1.3 is that basic handshakes take a single round trip compared to TOS 1.2, 2 round trips. The time it takes to connect to servers that support TOS 1.3 is reduced because of that, which means that web pages that support TOS 1.3 load faster in browsers that support the new standard. Security is improved as well in TOS 1.3 when compared to previous versions. TOS 1.3 focuses on some widely known and analyzed cryptographic algorithms, while TOS 1.2 includes support for more algorithms, of which some were exploited successfully in the past. TOS 1.3 encrypts most of the handshake next to that, which improves privacy when connecting to servers, as much of the information that is in the open when TOS 1.2 is used is now encrypted and unreadable while in transit. Although most of the vulnerabilities were addressed with the version of 1.3 of TOS, there are some vulnerabilities and some possible attack vectors that could be used against it. One of these attacks is also known as the Downgrade Attack on TOS 1.3. The Downgrade Attack leverages a sidechannel leak via cache access timings in order to break the RSA key exchanges of the TOS implementations. The attack affects all versions of TOS, including TOS 1.3, where the later version of TOS does not even offer an RSA key exchange. It uses state-of-the-art cache attack techniques, and of course it is very efficient. Two ways exist to attack the TOS 1.3, and in each attack the server needs to support an older version of the protocol. First technique relies on the fact that the current server's public key is an RSA public key, used to sign its ephemeral keys during the handshake, and the older version of the TOS that the server supports reuse the same keys. The second one relies on the fact that both peers support an older version of TOS with a cipher suite supporting an RSA key exchange. While TOS 1.3 does not use the RSA encryption algorithm for its key exchange, it does use the signature algorithm of RSA for it. If the server certificate contains an RSA public key, it will be used to sign its ephemeral public keys during the handshake. A TOS 1.3 client can advertise which RSA signature algorithm it wants to support between RSA and RSA PSS. As most TOS 1.2 servers already provide support for RSA, most will reuse their certificates instead of updating to the more recent RSA PSS. RSA digital signatures specified per the standard are really close to the RSA encryption algorithm specified by the same document. This enables the Blankenbacher decryption attack on RSA encryption to also work to forge RSA signatures. The attack can be carried if the new connection exposes a length of Blankenbacher oracle with a certificate using the same RSA key but for key exchange. Additionally, every TOS connection starts with a negotiation of the TOS version and other connection attributes. As the new version of TOS 1.3 does not offer an RSA key exchange, the exploitation of the attack must first begin with a downgrade to an older version of TOS. TOS 1.3 being relatively recent, most servers supporting it will also support older versions of TOS, which will all provide support for RSA key exchange. A server not supporting TOS 1.3 would thus respond with an older version, TOS version. For example, TOS 1.2. To downgrade a client's connection attempt, one can simply spoof the answer from the server. Besides protocol downgrades, other techniques exist to force browser clients to fall back onto older TOS versions. Network glitches, a spoofed TCP reset packet, a lack of response, and so on. This was a very brief overview of the TOS 1.3 vulnerabilities. There is a lot of information on the internet, and I hope you found this video interesting. If you like it, please hit the like button and subscribe for more videos, and I'll catch you in the next one. Thank you very much for watching.